to take one of the trickiest topics in chemistry, periodic trends, and it turned to a simple, powerful tool you can use to absolutely crush your exams. So, take a look at this question. It looks like a classic trap, right? Mixing up elements from different periods, different groups. But stick with me here because by end of this session, you're going to look at this and just know the answer in seconds. You see, the real secret to mastering the periodic table isn't just memorizing the trends. No, it is not. It is knowing the exceptions. It is understanding why the rules sometimes break. And that's exactly what we are going to dive into. Okay, first thing first, that is everything. And I mean everything we are about to cover. From ionization energy to acidity, it all starts with size. If you really get into this one concept, everything else just clicks. So let's lock this down. Think of it like a tug of war happening inside every single atom. You have got the positive protons in the nucleus pulling on the negative electrons. Now, a cation has lost an electron. So, the protons have an easier time to pull the remaining ones in tighter, right? An anion has gained an electron, which means the protons pull gets spread a little thinner, it weakening the grip on each one. And here is the direct result of that little tug of war, a cation, the protons big win. They yank those electron shells closer and boom, the atom gets smaller. For an anion, you have added the extra electron, so the proton just can't hold on as tight as before. Their grip weakens and the whole atom kind of puffs up and gets larger. So here is the crucial takeaway. The rule you can always count on. The more positive the charge, the smaller the ion. The more negative the charge, the bigger it gets. It is as simple as that. If you are comparing two ions of the same element, the one with the higher positive charge is always smaller. Alright, now we have size down. Let's see how it connects directly to another big trend, metallic character. And really, all that means is how easily does an atom give up one of its electrons. And the logic just flows perfectly from size as you go across the period left to right. Moving on the period left to right, atoms get smaller and hold on to your electrons tighter because of effective nuclear charge. And if you're going to down the group, the atoms are getting much bigger because those outer electrons are way out there, barely hanging on, which makes them easy to lose. So they become more and more metallic. So logically, you look at lithium, beryllium, and boron all right next to each other and think the ionization energy should just increase smoothly from left to right. Making sense? Doesn't it? But if you thought that, you have fallen right into the most common trap of this topic. That expected order is wrong. And understanding why it is wrong is the secret to getting these questions right every single time. And here is the little secret, electronic stability. You have to remember, nature always just loves balance. It obsessed with it. Electronic configurations that are completely full or exactly half full are the VIPs of the atomic world. They are extra, extra, extra stable. The atom will fight to keep the perfect harmony. So let's trace the logic. First, look at beryllium. It has full, stable 2s orbital. It is happy enough. Now look at boron right next door. It has this one lonely electron in its 2p orbital just waiting to be plugged away. So because beryllium is so stable, it actually takes more energy to break into that full orbital than it does to just snatch the boron's lone electron. And that's it. That's why the order flips. Beryllium's ionization energy is higher than boron's, and that's the exactly same logic explains the other famous exception. Nitrogen has a perfectly balanced half-filled 2p configuration, which makes it super stable. Oxygen has 2p electrons, that is 4 2p electrons, but think about it. If you remove one electron from oxygen, it achieves the super stable state, just like nitrogen. So it actually easier to ionize oxygen than nitrogen, right? But the trend flips again. Fantastic. Now that we have got the stability down, let's switch the gears to tackle acidity. I'm going to show you a simple trick that makes ordering oxides a common, really common exam question, which is incredibly easy. Here is the golden rule. When you're comparing oxides of the same element, don't overthink it. Just count the oxygen atoms. The more the oxygen you have pulling electrons away from the central atom, the more acidic the whole thing becomes. Just look at this series of nitrogen oxides. As you go from N2O to N2O3 to N2O5, what happens? The number of oxygen atoms goes up and the acidic strength goes right up with it. It is a straight shot. The chemistry behind this is all about the oxidation state. Oxygen is an electron hog. It pulls the electron density. It is very greedy atom, but not much as fluorine. Away from the central atom, so the more oxygens you add, the higher the central atom's oxidation state gets. In Mn2O7, manganese at its massive +7 oxidation state. That high positive charge makes it an incredible electron magnet, which is the very definition of strong acid. Okay, pay close attention to this one. This is a trend breaks the big rule, and it is an absolute favorite for trick questions. We are talking about the acidity of hydrides. For pretty much everything else, acidity decreases as you go down the group. But for hydrides, and only for hydrides, the rule is flipped completely on its head. Acidity actually increases as you go down the group. So, why does this happen? We all know fluorine is the most electronegative element, so you would think HF would be the strongest acid. But with hydrides, size wins. As you go down the group, the atoms get much bigger. This means the bond between hydrogen and iodine is way longer and weaker than short, strong bond in HF. A weaker bond is easier to break, which makes it easier to release a proton. That is why Hi is the strongest acid in the group. For hydrides, just remember big is more acidic. So we have hit the key rules and more importantly, the critical exceptions also. Let's pull all together right now. And here it is your ultimate cheat sheet. We have got size, ionization energy, metallic character, and acidity. And look, we have even added the thermal stability for carbonates. These questions are asked multiple times in your exams. Turns out that it depends on size. You can see the trends. A small beryllium ion weakens the carbonate and so it decomposes easily with heat. A big barium ion does not, so it's much more stable. Can you see the pattern? Almost every trend comes back to size, but the real skill is spotting those exceptions. Feel free to pass here and use this to see the big picture of this and take a screenshot. And that's a really whole point of this session. Don't just be the machine just memorizing the trends. Understand the logic. When you know why the full orbit makes the beryllium so stable and why that long weak Hi bond makes the hydroiodic acid so strong, you can't be tricked. You can solve any problem they throw at you. So let's circle all the way back to where we started with the challenge. But now you have the tools. Look at these problems. For each one, ask yourself, is it an hydrate or an oxide? Are we going to down a group or across a period? Which rule applies? Or which exception applies? Pause the video and solve them. Tell me the answer in the comment section below. You know, the logic is clear to you now. You have got this. Let's see in the next video.